Implicit Solutions, Level 3. In this video, we're going to continue illustrating how to verify implicit solutions to ordinary differential equations. This time around, we're going to go over slightly more challenging examples. Let's go ahead and take a look at the first example. Verify that the indicated function is an implicit solution to the differential equation. If possible, find an explicit solution. Give an interval I of definition for each explicit solution. The differential equation is 2xy plus the quantity x squared minus y times y prime equals 0. And the implicit solution to verify is negative 2x squared y plus y squared equals 1. Alright, like in the previous video, let's go ahead and take the derivative of this implicit function. Taking the derivative and applying the product rule along with the power rule, we obtain the following expression. Next, we need to isolate the derivative term, in this case, y prime. In order to accomplish this, we need to move all the terms containing y prime and move them to one side of the equation, and the rest of the terms to the other side of the equation. Doing that, we obtain the following. The whole point of moving all the terms to one side is so that we can factor out the y prime term, as follows. From here, it's just a matter of solving for y prime. Doing that, we obtain the following expression. Having found the derivative, we proceed with the substitution step. Let's verify that the left and right-hand side of the differential equation are equal to each other. Carrying out the substitution, we obtain the following expression. Next, we go ahead and simplify the expression. Let's first distribute the quantity x squared minus y with 4xy, as follows. Then, let's go ahead and add both terms together. We're going to need to find a common denominator, and then proceed by adding the numerators. Doing that, we obtain the following expression. Simplifying the numerator, we see that all the terms cancel out, leaving us with 0 over the quantity negative 2x squared plus 2y, which simplifies to 0. Both sides of the differential equation are equivalent, hence this implicit relation is a solution to the differential equation. Next, let's go ahead and assign an interval of definition. We first need to generate the graph of this implicit solution. This implicit function is probably not familiar to you, since it does not have the form of any conic section. So let's see if we can find an explicit solution. Notice that at first glance, it seems like it is plain impossible to solve for y, since we have two terms with this variable, and one of them is raised to the power of 1, and the other is raised to the power of 2. How can we possibly solve for y? It turns out that we can actually accomplish this. First of all, notice that the implicit solution contains a quadratic term, a linear term, and a constant term. Let's rewrite this expression by moving all the terms to one side of the equation, and setting the other side of the equation equal to 0. Lastly, let's rewrite the terms with the powers in descending order, as follows. This implicit function is essentially a quadratic equation of the form ax squared plus bx plus c equals 0. But in this case, instead of x representing the variable, we have y taking the place of the variable x. This means that we can use the almighty quadratic formula and find an explicit solution. The coefficient a, b, and c will be equal to 1, negative 2x squared, and negative 1 respectively. Substituting these expressions into the quadratic formula, we obtain the following expression. Simplifying throughout and dividing both terms by 2, we obtain the following explicit solutions. Y equals x squared, positive negative, the square root of x to the power of 4 plus 1. Next, let's go ahead and plot both of these solutions. The positive solution generates the following graph. The domain of this function is essentially all real numbers, from negative infinity to positive infinity. And this will also serve as our interval of definition. If we use the second explicit solution, we obtain the following graph. This function is also defined from negative infinity to positive infinity, and this interval also serves as an appropriate interval of definition. In this example, we had an implicit solution that was quadratic in form, and therefore, we were able to find an explicit solution by solving for y in terms of x via the quadratic formula. Alright, let's go over the final example. The differential equation is y prime equals the quantity negative 2x minus y over the quantity x plus 2y. And the implicit solution to verify is y squared plus xy plus x squared equals 0. Alright, like always, let's first find the derivative of this function. Taking the derivative implicitly and applying the power rule along with the product rule, we obtain the following expression. From here, it's just a matter of solving for the derivative. To accomplish this, we're going to need to move all the terms containing y prime to one side of the equation, and the rest of the terms to the other side of the equation, as follows. Next, we go ahead and factor out the y prime term. From here, we go ahead and solve for y prime by dividing both sides of the equation by the quantity 2y plus x, as follows. Having found the derivative of the implicit relation, let's go ahead and substitute this expression into the differential equation. Substituting the expression, we see that this implicit relation is a solution to the differential equation. Next, let's check to see if we can find an explicit solution. Notice that this implicit relation is quadratic in form. It contains a quadratic term, a linear term, and a constant term. In order to solve for y in terms of x, we're going to need the quadratic formula so we can find an explicit solution in terms of x. The coefficient a, b, and c will be equal to 1, x, and x squared respectively. Substituting these expressions into the quadratic formula, we obtain the following. Simplifying the expression inside the square root results in the following expression. Y equals negative x positive negative the square root of negative 3x squared over 2. Having found an explicit solution, we are ready to graph the expression and find an appropriate interval of definition. Unfortunately, we have a problem. Notice that the domain of the radicand is always going to yield a negative number, except at x equals 0, and as a result, we are forced to take the square root of a negative number. This explicit solution is not a real valued function. Since we do not have a real valued function, we cannot assign an interval of definition. In the end, this implicit relation is a formal solution to the differential equation. We cannot say that this implicit relation is a solution to the differential equation since we cannot assign an interval of definition. Keep on the lookout for implicit solutions that formally satisfy a differential equation. To truly determine if an implicit relation is a solution, we need to be able to determine an appropriate interval of definition. So keep this little detail in mind. Alright, in our next video, we will go over the concept of a family of solutions.